Welcome to The Explainer. Today, we're going to pull back the curtain on a legendary computer science paper, one that discovered a fundamental and, honestly, a kind of shocking truth about how computers cooperate. It's a secret that underpins, well, pretty much our entire digital world. So let's start with a question. What if one slow computer could bring a whole system to a grinding halt? I know, it sounds a little dramatic, right? But this single question is at the very core of a huge problem in computer science. It's a puzzle that the people who build your bank's database, the cloud, even cryptocurrencies, they all have to solve this every single day. All right, so before we get to the impossible part, we really need to understand what the goal is in the first place. And at the heart of this whole challenge is something called the consensus problem. So what does that actually mean? Well, basically, it's about getting a bunch of separate, independent computers to all agree on a single truth. Even if they start out with different information, they absolutely must land on the exact same final decision. That's the only way to keep the systems we rely on consistent and correct. And believe me, this is not some abstract theoretical thing. It is the invisible foundation of our digital lives. I mean, think about it. When you book the very last seat on a plane, a whole bunch of computers have to agree that you got it, and not the person who clicked a millisecond after you. When you move money, the bank's computers have to agree, yep, the money left this account and arrived in that one. Without consensus, all of this would just be total chaos. Now, in a perfect world, if computers never ever crashed and messages showed up instantly, this would all be super easy. But we don't live in a perfect world, do we? We have to deal with the absolute messiness of reality. And this brings us to the big twist. This is the one condition that changes absolutely everything. Let me introduce you to the villain of our story, the asynchronous network. This line just nails the core challenge. See, a synchronous system, that's like a perfectly conducted orchestra. Everything happens on cue at a predictable pace. But the real world, and especially the internet, it's asynchronous. There are no synchronized clocks. There are absolutely no guarantees on how long a message will take to arrive. It's really like putting a message in a bottle, tossing it in the ocean, and just hoping for the best. You have no idea when or even if it'll ever get there. And this right here, this is the whole problem. In a purely asynchronous world, you can never, ever be certain if a computer you're waiting on is just being incredibly slow or if it has completely crashed. There is just no way to tell the difference. And that uncertainty, that's the key to everything. So with this deep uncertainty floating around, 3 researchers, Michael Fisher, Nancy Lynch, and Michael Patterson, they asked a really simple but incredibly critical question. Can we design a protocol that guarantees we'll reach consensus in this unpredictable world, even if just one computer might fail? And the year they dropped their bombshell of an answer was 1985. In a paper that would literally change distributed computing forever, they laid out a proof that was as elegant as it was just devastating. Their conclusion was just devastatingly simple. They proved with pure math that it was impossible. No algorithm, I don't care how clever it is, can guarantee that it will ever reach a decision if there's even a tiny chance that a single one of those computers might crash. The system could just run forever, never making a choice. And just like that, this stunning discovery became known as the FLP impossibility result, named after its authors, of course. And it stands today as one of the most important theorems in all of distributed computing. So you're probably thinking, how on earth is that possible? To get why it's impossible, we don't actually have to dig through all the dense math. We can just use a pretty simple analogy. Okay, so imagine the system is in what's called a bivalent state. All that means is the final decision could still go either way, like commit or abort. The proof so cleverly shows that you can always create a situation where the system is balanced on this knife's edge. A single crucial message gets sent, but its delivery can be delayed for who knows how long. And because the other computers can't tell if the sender has crashed or is just being super slow, they can't safely make a final decision. I mean, if they decide too early, they could cause a massive error. So they wait, potentially forever. The original paper used diagrams kind of like this one to show the heart of the paradox. What it's demonstrating is that by just slightly changing the order that messages get delivered, you can lead the system down completely different paths. The proof shows it's always possible for the network to deliver messages in just the right, or I guess the worst possible way, to trap the entire system in a state of permanent indecision. Okay, wait a minute. If guaranteed consensus is theoretically impossible, how does your bank transfer actually go through? How does the modern internet even work at all? Are all our systems just one delayed message away from freezing forever? Well, the short answer is that real-world systems get around this theoretical brick wall by, well, essentially by cheating. They relax the super strict, purely asynchronous rules that were used in the proof. They basically sneak a little bit of that perfect world timing back into the equation. So, what do these cheats look like? Well, the most common one is the timeout. A system just decides, hey, if I don't hear back in, say, 5 seconds, I'm just going to assume the other computer failed. Now, this breaks the pure asynchronous model because you're making an assumption about time, but it works incredibly well in practice. Other strategies use randomness to make the odds of getting stuck in that perfect storm worst-case scenario vanishingly small. And that's really the big lesson here, right? Engineering is often the art of finding these brilliant, practical solutions to problems that are, on paper, theoretically impossible to solve with 100% perfection. We trade that absolute mathematical certainty for systems that are reliable enough for the real world. We choose a system that works 99.999% of the time over one that is theoretically perfect but could freeze up at any moment. And that just leaves us with a final, kind of wild thought. The FOP Impossibility results is this amazing reminder that the smooth, reliable digital world that we all depend on is, in many ways, a very clever illusion. It's a practical masterpiece that's been built right on top of a fundamental, unsolvable paradox.